located about 2.5 million light-years away. Andromeda, our nearest galactic neighbor, is far more than a glowing cloud of stars. It's a vast cosmic city, holding billions of suns and, more intriguingly, secrets that science has yet to fully explain. How can a supermassive black hole, estimated to weigh around 140 million times the mass of our Sun, exist at the very heart of this galaxy? Mysterious streaks of light, regions bursting with newborn stars. Every detail underscores the breathtaking wonder of Andromeda. Yet, perhaps the most astonishing revelation is a prediction that sends chills down the spine. In roughly 4 billion years, Andromeda and our Milky Way will collide and merge, forming a colossal elliptical supergalaxy. This isn't speculation. It's confirmed by Hubble's observations and decades of research tracking the motions of stars in both galaxies. But the story doesn't end there. Scientists have uncovered evidence of ancient galactic collisions, overwhelming dominance of dark matter, and unusual isotopic ratios in Andromeda's stars. These findings hint at a narrative that stretches beyond time and space, one that challenges everything we thought we knew. This marvel is more than an astrophysical puzzle. It's an open invitation to those who dare to understand the infinite cosmos. Join us on this journey of discovery, where Andromeda is not just a galaxy, but a profound mystery waiting to be unraveled. At the dawn of the 20th century, most scientists believed the universe consisted of only one galaxy, our Milky Way. Objects like the Andromeda Nebula were thought to be mere clouds of gas within our own galaxy. The concept of a vast universe teeming with hundreds of billions of independent galaxies had not yet entered human imagination. Then came 1920, a pivotal year marked by the great debate between two leading astronomers, Harlow Shapley and Heber D. Curtis. Shapley argued that the universe contained just one galaxy, with the Sun positioned near its center. Curtis, however, held a radically different view, claiming that nebulae like Andromeda were, in fact, separate island universes, galaxies far beyond the Milky Way. Just a few years later, Edwin Hubble set his sights on Andromeda. His observations led to the discovery of Cepheid variable stars, remarkable celestial beacons whose brightness pulses in a precise, predictable cycle. This relationship between their pulsation period and intrinsic brightness allowed Hubble to calculate their true distance. The result was staggering. Andromeda was not a gas cloud within the Milky Way. It was an entirely separate galaxy, a colossal system located about 2.5 million light-years away. The result was staggering. Andromeda was not a gas cloud within the Milky Way. It was an entirely separate galaxy, a colossal system located about 2.5 million light-years away. Hubble's revelation shook the foundations of human understanding. Overnight, our perception of the cosmos transformed. The universe was no longer a single galactic island, but an infinite ocean filled with hundreds of billions of galaxies, each harboring billions of stars and potentially countless worlds like our own. From believing ourselves at the center of everything, we suddenly became a speck of dust in an endless expanse. The question was no longer, what is Andromeda, but rather, if Andromeda is just one among billions, how vast is the universe truly? Studying Andromeda doesn't just reveal the nature of this galaxy, it reflects back insights about our own Milky Way. Andromeda is a spiral galaxy, similar in form but far more massive, roughly 1.5 times larger, stretching an estimated 220 light-years across. Seen from afar, it resembles a luminous spinning disk with a blazing core at its center. At the heart lies the central bulge, a dense spheroidal region filled with ancient stars more than 10 billion years old. Andromeda's bulge is vast and brilliant, a stellar metropolis. Like most massive galaxies, it harbors a supermassive black hole, revealed by the orbital dance of surrounding stars. Its mass is estimated between 100 and 200 million times that of our Sun. Though it emits no light, this invisible gravitational engine commands the motion of Andromeda's core. Extending outward are its spiral arms, graceful arcs of starlight entwined with ribbons of dust and hydrogen gas, perfect nurseries for star formation. Within these sweeping arms, stellar birth is relentless, forging generation after generation of stars that renew the galaxy. Surrounding it all is the stellar halo, a faint spherical envelope encasing the disk and bulge. Here lie the galaxy's oldest stars, often gathered in globular clusters, ancient relics of the early universe or remnants of smaller galaxies devoured by Andromeda in a violent past. Studying this halo unlocks clues to the galaxy's turbulent evolution. Yet the most enigmatic feature of all is dark matter. Observations suggest that up to 80% of Andromeda's total mass is invisible. We cannot see it, but its presence is undeniable, betrayed by the puzzling speed of stars orbiting at the galaxy's edge. If only normal matter existed, these stars would drift sluggishly under waning gravity. Instead, they whirl far faster than expected, evidence of an unseen substance creating a gravitational grip strong enough to hold the galaxy together. This confirms a profound truth. Without dark matter, we cannot comprehend the architecture or dynamics of Andromeda. Invisible yet powerful, it shapes, stabilizes, and sustains this majestic system. When we gaze upon Andromeda, we are not merely observing starlight, we are confronting the unseen. Here, in its depths, the universe conceals some of its most profound secrets about the very nature of matter itself. The structure of Andromeda is not the result of a single, orderly formation, but the product of a violent and chaotic past, defined by catastrophic collisions with fragments of other galaxies. The clearest evidence of these collisions lies in the strange streams of stars and irregular orbits observed within Andromeda's halo, revealed by modern telescopes like Subaru and Hubble. Instead of moving in a uniform pattern, some star groups drift along distinct paths or follow bizarre trajectories that defy explanation. Unless this galaxy once devoured others, in fact. Scientists believe Andromeda consumed at least one or two smaller galaxies in the distant past. One striking example is the giant stellar stream, a massive ribbon stretching over 130 light-years, thought to be the remains of a dwarf galaxy torn apart about 1 billion years ago. These disrupted orbits and asymmetric mass distribution stand as silent witnesses to an age of cosmic violence. When a smaller galaxy is drawn into a larger one, immense tidal forces rip it apart, scattering its stars and gas into elongated streams before slowly absorbing them into the greater structure. And the process is far from over. Today, Andromeda remains the dominant core of a system containing more than 20 satellite galaxies, many of which are being stretched and distorted by its gravity. Messier 32, an ultra-compact elliptical dwarf galaxy, is tiny yet astonishingly dense with stars, its shape a testament to intense gravitational interactions. Another, Messier 110, a larger elliptical dwarf, bears its own scars under Andromeda's influence. The implications are profound. Andromeda's present form is the dynamic outcome of countless violent mergers. It stands as living proof of a universe sculpted through collisions, a cosmic dance where large galaxies grow by consuming smaller ones, forging the grand structures we see today. Andromeda has not only survived these storms, but has thrived because of them. Yet these signs of past collisions are more than echoes of history. They are omens of what is to come. A far greater event looms ahead, inevitable and unstoppable. The collision between Andromeda and the Milky Way. This is no longer the story of the past. It is our destiny. The stars within Andromeda carry the chemical record of the galaxy's entire history. By decoding the wavelengths of light it emits, through the science of spectral analysis, astronomers have uncovered extraordinary clues. In Andromeda, hydrogen and helium, the two primordial elements forged in the Big Bang, dominate its mass. forming the raw material for the galaxy's earliest generations of stars. Their abundance reveals that much of Andromeda's matter traces back to the very dawn of the universe. Yet the true intrigue lies in heavier elements. Iron, carbon, oxygen, nitrogen, the essential ingredients for life. These were absent in the infant cosmos. They were born in the fiery deaths of massive stars. When such giants ended their lives in spectacular supernovae, they seeded space with clouds rich in metals. These remnants later coalesced into new generations of stars and planets. The presence of these metals in Andromeda signals a history shaped by countless stellar life cycles. Creation, death, and renewal across billions of years. Even more compelling is the discovery of unusual isotope ratios in some of Andromeda's stars and gas. Rare variants like carbon-13, neon-22, and iron-60. Isotopes are forms of the same element with differing numbers of neutrons, and their distribution reveals the very processes that forged them. These distinctive ratios suggest Andromeda's stellar evolution followed a unique path, perhaps markedly different from that of our own Milky Way. It is not merely a colossal repository of matter. It is a vast archive of the universe's nuclear history, written across its stars. And now, as we begin to piece together Andromeda's internal story, a far greater question emerges. What will happen when this entire galaxy collides with the Milky Way? No longer a question of past or structure, but of an impending cosmic future. A future not imagined, but inevitable. If the chaotic galactic collision between the Milky Way and Andromeda unfolds as predicted, it could leave behind an astonishing consequence: the emergence of countless rogue planets. These are not worlds orbiting a star like our Earth, but planets flung from their home systems by the violent gravitational chaos of merging galaxies. Cast adrift in the eternal darkness of interstellar space, they would no longer receive light or heat from any sun. Their surfaces would freeze solid, their temperatures plunging near absolute zero. A bleak and desolate vision of icy, lifeless spheres. But this is no longer a hypothesis. Observations from the Subaru telescope and sky surveys, such as OGL, have detected dozens of these free-floating planets, unbound to any star. based on gravitational models and stellar density. Scientists estimate that billions of rogue planets could exist within our galaxy alone, a number likely to surge after the Great Galactic Merger. Yet, here is where the mystery deepens. Our familiar definitions of life may no longer apply. Despite the absence of sunlight, some rogue planets might still harbor conditions favorable for life. If a planet is massive enough to retain internal heat generated by radioactive decay, or if it is a giant gas planet with moons locked in tidal embrace, like Europa orbiting Jupiter, then liquid water could persist in hidden oceans beneath layers of ice, warmed by geothermal energy. This opens a profound question. Could life, whether in the form of simple microbes or something far more complex, survive and even thrive in the eternal night of these sunless worlds? Such a life would not rely on photosynthesis, but perhaps on chemosynthesis, drawing energy from hydrothermal vents deep within alien seas, or from other geothermal sources, sustaining ecosystems in the darkness. The collision between Andromeda and the Milky Way will not erase everything. Instead, chaotic gravity will churn and blend colossal reservoirs of matter massive clouds of gas, dust, and most intriguingly, complex organic molecules, the fundamental building blocks of life such as amino acids and nucleobase precursors, will be scattered across this newly forged universe. Carried from regions that may have once nurtured life to uncharted, untouched realms, they will traverse the cosmic expanse Scientists refer to this process as intergalactic panspermia. An alluring hypothesis suggesting the spread of life's ingredients across the cosmos. Spectroscopic studies from the Spitzer and Herschel space telescopes confirm a striking pattern. In galactic collision zones, gas and dust densities surge dramatically. Igniting colossal star-forming regions known as starburst zones. Within these violent cradles, astronomers have detected complex organic molecules, formaldehyde, methanol, and even simple amino acids. The very ingredients that fuel the chemical evolution leading toward life. Their presence within colliding stellar clouds is no longer a surprise. But a revelation of cosmic chemistry at work. Ironically, the turbulence and compression wrought by gravitational upheaval create the perfect conditions for stellar genesis on an explosive scale. New stars, new systems, fresh territories where life might find a foothold. Emerge from the wreckage. Likewise, the galactic collision, despite its ferocity, will transform Milkomeda into a fertile cosmic plain. A landscape of new beginnings where unprecedented conditions may arise to nurture the next generations of life, in forms and places beyond our imagination. It is a paradox of destruction and renewal, a profound testament to the resilience and adaptability of life in the vast, unyielding universe. And when these scattered seeds of matter settle into their new gravitational homes, another question emerges. Can life endure when the very boundaries of habitability shift? In this cosmic upheaval, not only matter but the architecture of survival itself will be rewritten. And that is the story the next chapter will reveal. When the seeds of life might be sown through galactic collisions, a profound question arises. Will the physical conditions in this newly formed galaxy remain favorable for life to thrive? Life does not merely require raw ingredients, it demands stability. A sanctuary where radiation is not lethally intense, and where heavy elements abound to build the molecules essential for biology. In astronomy, this region is known as the galactic habitable zone. a theoretical ring encircling a galaxy's center, where conditions are considered most suitable for life to originate. Evolve into complexity and endure over cosmic timescales. This zone is defined by key criteria rooted in astrophysical and chemical studies. First, it must be far from catastrophic events, supernova explosions that can unleash torrents of gamma and X-rays. Sterilizing everything within tens or even hundreds of light years. Second, it must contain sufficient heavy elements: carbon, oxygen, nitrogen, iron, silicon. The raw materials necessary for rocky planets like Earth and the intricate organic molecules upon which life depends. But after the colossal merger of the Milky Way and Andromeda, this architecture will be dramatically rewritten. Starburst regions will ignite in areas once calm, while stellar density will fluctuate wildly. Rising in some regions, plummeting in others. The implication is clear: the galactic habitable zone will shift dynamically. Conversely, regions once too barren or bathed in deadly radiation may fall into the new zone of safety. a domain of balanced physics, temperate conditions, and starlight gentle enough for photosynthesis to flourish. The impending collision is not an ending, but perhaps a dawn. A renaissance for life within a future supergalaxy. And yet, as this habitable zone is redrawn, the ultimate question lingers, not of galaxies or distant worlds, but of us. When this cosmic encounter unfolds, where will humanity be? Will we remain here, or will we have mastered the art of voyaging beyond the solar system? Carrying with us the memory of a galaxy that once was? As the galactic habitable zone shifts, reshapes, and redefines the conditions for survival, one question looms. If humanity endures long enough on Earth to witness the monumental collision of the Milky Way and Andromeda, what will this mean for us? This will not merely be an astronomical event. It will be the ultimate test of human intellect, resilience, and adaptability. We are speaking of a future some 4 billion years away. A timescale so vast that human evolution and technology could ascend to heights unimaginable today. Yet, within that distant chaos, another question emerges. Will we master the power to move beyond danger? With sufficiently advanced technology, could we develop propulsion systems fast and safe enough to escape the collision zone, venturing into other star systems, perhaps even beyond the bounds of our original galaxy. Such ambitions demand leaps beyond our current understanding, propulsion breakthroughs, life support systems capable of sustaining journeys that span millions of years. And the discovery of new worlds to call home. Alternatively, could we protect Earth itself or migrate within the emerging supergalaxy, Milky? Or even leap to other galaxies if technology allows? Studies from Princeton University and the SETI Institute propose an extraordinary solution if a civilization becomes advanced enough. Humanity could construct artificial habitats, self-contained, mobile ecosystems carrying air, water, and biospheres, shielded from the unpredictable nature of the cosmos. But even if such grand engineering remains out of reach, adaptation will remain our greatest weapon. As planetary scientist Sarah Seeger suggests, if Earth-based biology can learn to survive without gravity, endure intense radiation, or thrive in darkness without sunlight, then future humans, engineered or evolved, may persist in the vast landscapes of a merged galaxy. We have survived ice ages, cataclysmic asteroid impacts, and mass extinctions. Yet we have never faced change on a galactic scale. Should we overcome this event, humanity will transcend its identity as mere dwellers of Earth. We will become witnesses and survivors of the cosmos. Chroniclers of the grandest chapters in galactic history. The story of Andromeda is not simply a tale of a distant galaxy. It is a mirror reflecting the uncertain, awe-inspiring future of our own existence. The journey to understand Andromeda is far more than the study of a galaxy. It is an epic tale of relentless transformation. We have traced its turbulent past, marked by colossal collisions, and seen how those violent encounters sculpted the intricate, majestic structure we observe today. We have glimpsed a distant future where our Milky Way and Andromeda will merge in a cosmic dance spanning billions of years. A future that heralds an era of reconstruction, where the old is dismantled to lay the foundation for the new. As we look toward the destiny of Milkomeda, we envision the reconfiguration of our local cosmic ecosystem. Matter will reorganize, habitable zones will shift, and perhaps within billions of emerging star systems, a new Earth may be born. Not as a mere replica, but as an heir. This truth reminds us that even in the grandest upheavals of the universe, there is hope, there is life, there is renewal. It compels us to reflect on our place within an ever-evolving cosmos. And on the adaptability that life must embrace to endure. The story of Andromeda, from its earliest mysteries to the vision of a future collision, is a powerful reminder that the universe is an infinite frontier. Each discovery pulls back the veil on one mystery, only to reveal countless more. This is not just science, it is inspiration. It is the boundless curiosity that drives us to imagine what lies beyond the farthest edges of our understanding. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.